Every classification algorithm we've seen so far has one limitation. What if the data simply can't be separated by a straight line? What if the pattern is far more complex? For years, that was one of the biggest problems in machine learning. Then researchers found a surprisingly elegant solution. Instead of changing the classifier, they changed the space the data lived in. That idea became the support vector machine. Imagine you have two groups of data. Your goal is to separate them with a line. There are many possible lines. But support vector machines don't choose just any one. They search for the line with the largest possible margin, the widest safety gap between the two classes. Why? Because a larger margin usually leads to better generalization on new data. But then researchers ran into a much bigger challenge. What if no straight line can separate the data? At first, this seems like the end of the story. But instead of changing the decision boundary, they changed the space the data lived in. They transformed the original features into a much higher dimensional space. In that new space, data that looked impossible to separate could suddenly become linearly separable. The amazing part is that the algorithm never needs to explicitly build those enormous feature vectors. Instead, it relies on a mathematical shortcut called the Kernel Trick. Rather than computing every high-dimensional feature, it only computes the similarity between pairs of examples. Those similarities contain all the information the algorithm needs. This allows support vector machines to work in feature spaces with thousands, millions, or even infinitely many dimensions, without ever storing those dimensions directly. Researchers created different kernel functions for different kinds of problems. Polynomial kernels help model more complex relationships. Gaussian kernels became one of the most widely used because they can capture highly nonlinear decision boundaries. And suddenly, a simple linear classifier could solve problems that looked impossible in the original feature space. But real-world data introduces another challenge. Data is noisy. Sometimes there are outliers. Trying to perfectly separate every training example can actually make the model worse. So researchers introduced the Soft Margin SVM. Instead of forcing every example to be classified perfectly, it allows a few mistakes. In exchange, the model becomes much more robust and generalizes better to unseen data. That balance between maximizing the margin and tolerating small errors made support vector machines one of the most successful machine learning algorithms for many years. And that's the journey. Start by finding the widest possible decision boundary. Transform the data into a richer feature space. Use kernels to make impossible computations practical. And allow a few mistakes so the model learns patterns instead of memorizing noise. Those ideas made support vector machines one of the most influential algorithms in classical machine learning. But building a powerful model is only half the challenge. How do you know if it's actually good? How much data should you use for training? How much should you keep for testing? And how do researchers fairly compare different models without fooling themselves? Those questions led to one of the most important practices in machine learning: data splits, model selection, and cross-validation. And that's exactly what we'll explore in the next video.